Hello everyone, let's go ahead and take a look at the intersection of two or more planes. Now what we're going to focus on is the Cartesian form of planes. And the reason for that is that we want to use matrices and row reduction methods to analyze the system of planes. Okay, so let's go ahead and take a look at a situation where we have two planes, and notice that we have the Cartesian form of both of those planes. And what we can do, of course, is change it into its matrix form, an augmented matrix form. And what we can do is we can use row reduction properties to go ahead and analyze the relationship between those two planes. Now, let's go ahead and do two things at one time. We're going to take a look at both the augmented matrix form as well as the geometric interpretation so that we can hopefully make the connection between those two. Now there's only three situations that can happen when you have two planes. They are either going to be parallel, they're going to intersect in a line, or they're going to be coincident with each other. Now if we go ahead and take a look at the situation where the two planes are parallel to each other, how can we go ahead and determine whether or not they're parallel? Well, the first thing that we can do if we go ahead and take a look at the vector forms of the planes is that if we know that the normals are parallel to each other, then of course the planes are also going to be parallel to each other as well. Now we need to also be careful with this situation where the two planes are coincident or right on top of each other, because again the two normals are again going to be parallel to each other. So we're going to have to differentiate between those two. Okay, and then of course if the two normals of the planes are not parallel to each other, then we know that the two planes will intersect and create a line. Now, if we go ahead and take a look at the situation where we had two planes being parallel or coincident, if we just looked at the normals, we would not be able to tell whether the planes were in fact parallel or coincident. We would just know it's one of the two situations. Now, if we go ahead and take a look at our augmented matrix though, notice that what we will come out with our augmented matrix, if we use row reduction properties, is the last line will be 0, 0, 0, and 0. So 0 is equal to 0, which means that the two planes are going to be coincident. Now, how do we go ahead and determine whether they are just parallel? Is that we're just going to come up with something similar in the sense that we have 0, 0, 0, but then with this constant value over here, it is not going to be 0. And so you're going to have a false statement of 0 is equaling something that is not 0. And therefore we know that the two planes are going to be parallel. Now the other situation, of course, is, we said, when the two normals are not going to be parallel to each other, and therefore are going to intersect in a line. And remember that after our row reductions, we come up with something that looks similar to this. And then once we go ahead and set t being equaling to the z value, then we can solve for t, solve for y in terms of t, and then after that substitute it into our original equation so that we can come up with something in terms of t for all x, y, and z. And then of course we can go ahead and solve for the equation of the line. So what we have right now, right, we want to go ahead and take a look at planes in their Cartesian forms so that we can go ahead and use an augmented matrix to go ahead and analyze it. Of course, if we wanted to go ahead and analyze the interaction just by looking at the normal vector of the planes, we could do that as well. Okay, we'll go ahead and take a look also at what happens with three planes. Okay, I'll talk to you a little bit later. Bye. Okay, hello everyone. When we go ahead and start taking a look at what happens when we have three planes, things get much more complicated. And so what we're going to take a look at is we're going to look at the 8 different possible situations in class, because then we'll be able to see some visuals, we'll be able to talk a little bit more exactly what is actually happening with the augmented matrix and what the solution will actually be. But if we wanted to go ahead and kind of give a very general summary of how we want to go ahead and analyze a system of three planes and how they are interacting, we can basically go ahead and take a look at it from this particular perspective. If we were to go ahead and put the system of three planes into matrix form, in other words, AX is equal to B, there's basically going to have two situations. you're either going to come out with a determinant of A being equal to 0 or the determinant of A not being equal to 0. Now, if A is singular, then remember that we always come up with two different situations. We either have an infinite number of solutions or we have no solution. And remember that what we said is that in order to determine what happens between these two, we're going to have to take a look at the augmented matrix. Now, the reason why it becomes so much more complicated with three planes is because if you have a situation where the determinant of A is equal to 0 and you have an infinite number of solutions, well, the two possible cases that you can have is that a line is generated or a plane is generated. And we're going to have to actually see how that works out. Now, you could also go ahead and take a look at no solution, where you have no common intersection among all the planes. Now, that might sound very simple, but then remember, we have 8 different possible situations, and so 8 of those situations are going to have to fall into one of those categories there, in addition to this one here. Now, of course, this one here is something that we've already looked at, is if the determinant of A is not equal to 0 and A is not singular, then of course we come up with a unique solution, which is going to be a coordinate. So all the 3 planes are intersecting in one location. They're intersecting in other locations as well, but only 2 at a time. But we need to find the location where all 3 planes are intersecting at the same time, because that is going to represent the solution of the system of the 3 by 3 matrix equation there. Now, again, just to recap though, the tools that we're going to need in order to analyze this particular system, or this particular situations with regards to 3 planes interacting with each other, is we're going to have to take a look at the normal vectors of all the planes. Of course, the reason for that is we can very easily determine if planes are now going to be parallel to each other. In addition to that, we're going to also need to make sure to use the augmented matrix and row operations, in particular if the determinant of A is equal to 0 or A is singular, and that means that we have these 2 situations here. So what that means then is that for these 8 different possible situations, one of them is when the determinant of A is not equal to 0, therefore you come up with a coordinate. There's going to be 7 other situations that are going to fall within this situation, but we still need to be able to analyze it. We use the normal vectors as well as the augmented matrix and row operations to do so. So the best way to do that is at least get an idea of how this is all working out, and we'll take a look at those situations as we work through some of the problems in class. Okay, so we'll see you later. Bye-bye.